Hello folks and welcome back to Aunt Rosie's Topological Bake Shop. So before we start the video, I would like to ask you guys a quick question. Have you ever baked one of our mini recipes and asked yourself, well, wow, I made a great product, but I think I want to deconstruct it and maybe make something else out of the ingredients I have. And so is it possible for me, or rather for you, the viewer, to deconstruct a recipe and put aside its ingredients for another use? Well, the short form answer is yes. So for today's special episode of Aunt Rosie's Topological Bake Shop, we will be teaching you guys how to unbake a pastry you've made. So in this video, we're not assuming that you have any ingredients right now, but we're assuming that you have a pre-made recipe, as in a recipe that you've already constructed. So the goal of this video is for you to learn how to deconstruct a recipe into a set of ingredients. And so let's get to it. Alright, so we're here at our baker, and so supposedly your baker can also debake objects. So here's the general definition of a debake, quote unquote debake. A debake is a decomposition of our structure into a set of quote unquote ingredients, which are the things that compose it. Every minute thing that composes the thing you constructed are the ingredients, obviously. Let B be a construction with structure. So for example, this could be a donut, or this could be an end sphere that you have decided to construct with a certain topology. So with the structure S, so S can be a map, it could be a relation over the elements of B, or it could be a topology, most especially a topology. Okay, if B can be deconstructed into a set of standard objects A1 ... AN, such that the composition of all of this is B and S into a set R1 up to Rn of relations, constructions, structures over A, such that the same thing holds, that their composition equals A, or S, sorry. Then the debake of BS is the set A1 ... AN and R1 ... Rn. Now it is important for us to identify how many quantities of a specific object or ingredient we have in that list. Because if we just say, if we just keep repeating the object up to the amount of times it occurs in the recipe, by the rules of set theory, they all collapse onto a single object. So they all become just one object in that set, and so we don't get a meaningful sort of debake from it. So we have essentially collapsed an ingredient into only one quantity of it, and we don't want that to happen. So it's best if we attach, say, an integer, a positive integer, at the front of the say ingredient to say that it is 3 quantities of that ingredient. Okay, so let's make an example. Let's say I've baked my monster donut. So this is T to the m minus 1, and then this is also with let's say the product topology. So we're doing the product version of our monster donut. So, because T is composed of m to the minus 1 amounts of circles, okay, now recall that m minus 1 is precisely 196,882, because that's the topological dimension of the donut, not really geometric dimension. Because when we take a patch on its surface and try to see how many directions we can go, we can only go in mainly 4 directions, which gives us 2 degrees of freedom, or 2 dimensions. Okay. Well, that is for a torus of geometric dimension 3, or a 2 torus. That's why we call it 2 torus. All right. So T to the minus m is composed of the product from I equals 1 up to m to the minus 1 of S1 circles. Now, according to our definition, we can break this down into multiple copies of S1. In fact, m minus 1 copies of S1, or 196,882 copies of S1 in our as they live in R2, well, separately, I can decompose t to the m minus 1 into a set, right, of this s1, multiple s1s, but I will index them this time. Instead of only attaching an integer to one s1 and then sort of try to make sense of that or make a definition out of that, what I can do is index the sub-object or the ingredient. And that index, or the final index, n, would be the amount of ingredients as stated there. So the thing is, if you have one ingredient and another ingredient that's distinct from that one ingredient, it's best if you sort of use the symbol for it, alright? So we cannot just say this ingredient, or we cannot just say ingredients and then times this, alright? You gotta specify what exactly are the objects in your set. Okay, so by the definition, I can deconstruct t to the m minus 1 into a set s1 1, s1 2, all up to s1 m minus 1, or s1 196882. Now, as I said a while ago, the reason why I put subscripts, or why I put subscripts here is because it differentiates one element here from another. Although they are exactly the same, topologically speaking, we want to distinguish one from another in the viewpoint of deconstructing our structure. And this symbol over here, that composition symbol, is a stand-in for any operation that combines sets or certain objects such that they become our structure B or our set B. So in this case, our operation between S1, S2, and so on is the Cartesian product. Okay, so the Cartesian product of all of these circles. So, right. And you'll notice that, of course, as written in the definition, S11 cross S12 cross dot dot dot, I can write all of the S1s. S1 to the m minus 1 is in fact equal to t to the m minus 1, according to how we constructed it in the first place. Alright, well, it's not enough to say that this set here is the set of all ingredients, because we still have to account for the topology here. Alright, and what I neglected to mention in my video constructing this object is that the product topology carries a subtopology in it. Okay, and this is what I mean by deconstructing the structure S over A into standard pieces or substructures. Because it's not enough to say, okay, I have the product topology over these circles, right? Or I have the product topology over this t here, or this t to m minus 1. It's not enough, because within those open sets inside that topology, each of these open sets have another layer of topology to them, because they are also open sets, or supposedly they should be open sets of R1, which, if you check the quotient version of our monster donut, you'll see that we have constructed the torus out of R1. And in fact, S1 here, each S1 exists as a subset, so S1 1, S1 2, they all exist within R2 space. And so that carries with it a layer of topology. And I explained that it was the Euclidean topology. So what we're going to do is take our topology Tx, which is of course all open sets U 1 cross dot 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 new m minus 1, such that each new I inside this product is open inside the topology of R. Because each of these open sets are inside the S1s over here. So the topology, oh no, R2 rather. And the topology over R2. So what we're doing now is deconstructing this into its sub-topologies. So this here is some new this new, oh no, this is, sorry, this is S1. Okay, and this is topology S1. Yeah, because this is defined for this stores. Okay, sorry for the error. All right, so this topology here would be two open sets, I believe, or no. This one here could be either quotient topology, or it could be a subspace topology. I'm gonna pick the subspace topology. So here's another important thing. Okay, when you're deconstructing a recipe, right, you can pick an arbitrary new amount of ingredients here. So even though you started out with a, let's say we started out with making S1 out of the quotient topology, by quotienting the unit interval with the points 0 and 1. Okay, you can also pick a different one. So even though I picked that quotient topology, when I deconstruct the structure, I can pick the subspace topology. So every open set inside R intersect every open set inside S1. All open sets inside S1 such that, intersections, I mean, of open sets inside S1 and in R2 such that, well, of course, the open set, those open sets we intersect with our open set is open inside the topology of R2. So I'll call it a new intersect a omega such that omega is open inside the topology of R2. And then now the topology of R2 is nothing but a set of open sets nu1 cross nu2 such that nu1 2 is open inside the topology over just R. Okay, and well, again, you can pick a different topology for TR here, but you'll notice that when you actually do this in the beginning, when you're actually constructing the thing, you will get a different variant or different flavor of course, our monster donut. So I now have all of my topologies here, and when I combine them all together, I put this inside here and I put this inside here. They're all sort of sequentially constructed and defined, or recursively defined over each other. The set now, or our deconstruction of Tx under this debake, would be the set, of course, itself, Tx, T S1, and T of R2. And so this is it. And then what we just do in the last step of debaking is take this set and union it with this set. So the final debake of the structure T to the m minus 1, and of course our Tx, is the set S1 1 up to S1 to the m minus 1, and then the three topologies, the product topology, the subspace topology of S1 with respect to R. So nu here is a subset of S1 and omega is a subset of R2. And then lastly, the topology over R2 and the topology over R, which can be the Euclidean topology. So there it is. This here is our list of ingredients. And so you notice that even though I constructed a different version here, using fewer ingredients in the last lecture, or actually the last recipe video, you've noticed that I've came out with more ingredients. So that's one thing you need to be careful of if you want to maybe duplicate your ingredients. You get to do this sort of thing by picking a different choice for every ingredient then. But of course, the best thing to do to conform with what you've done in the construction of your baked good is that, of course, you follow the ingredients you had and then you just list them into a set, of course. So in the product topology video, that would just be rather all S1s, right? S11 up until S1 to the m minus 1, and a product topology. And of course, the rest can be sort of a part of that Tx there, because we already said in the video that this ingredient needs to be well defined. So by well defined, which means what are the subtopologies we need in that topology, and we've already defined them here, and then we've explicitly written them down So essentially, these two are sort of equivalent to each other because these last three topologies that I've listed here are essentially just sub ingredients of this here. So we have not sort of duplicated anything or lost anything, but rather we have just expanded things. Because I neglected to expand things in the actual episode where I baked this thing. So, as an example of debaking, um, so the same thing would apply if we were to try a quotient topology. So if let's say I used my quotient variant of my donut, instead I would be of course using quotient, and then maybe I can pick a different choice for the topology, but it would rather be the same thing because it would all be contained inside the quotient topology, which is well defined. So that'll be it for this debake thing. So remember the general definition of how to debake. It is a decomposition of our given structure into a set of ingredients which composes the structure defined over a set, which is our ingredients. And so that is it for this episode. So I understand it was a bit more abstract than usual, and maybe I committed some mistakes here. If I made any mistakes, please make sure to comment them down in the description below. And so, apart from that, hope you guys have a good day and stay safe out there.